Okay, so good morning, and welcome back to Classical Mechanics 1. I believe many of you have come to CMI now for the first time, so I'd like to welcome all of you. So today is our 15th lecture, 20th of September, Tuesday, 2022. Okay, while we start, do we have any questions? Okay, so last time we spoke about a few different things. One was just mention briefly what we mean by the words dynamics, kinematics, and statics. Yeah, dynamics is basically time evolution of a system as determined by the forces that are in operation. Statics are situations where things basically don't move. State of the system doesn't change with time. Kinematics are aspects of the system that do not depend on the forces, but on other aspects like the number of degrees of freedom, frame of reference, range of variables, things of that sort. Okay, then we briefly discussed dimensions of physical quantities and said that every physical quantity could be assigned a dimension, which is a power of mass, power of length times the power of time, and those exponents could be determined. And we looked at a few examples. We'll do more. For instance, an angle was dimensionless. We also spoke about the two most commonly used systems of units, CGS and SI. We spoke of several examples of forces, gravitational force of Newton, the inverse law square character, the use of the superposition principle to determine the force due to an extended object like a spherical shell on point masses. We also spoke about the acceleration due to gravity. It was defined in terms of the force of gravity of the Earth on an object. We had defined the weight of an object as the force of gravity, force of the Earth on that object. And now we also defined the acceleration due to gravity as that force divided by the inertial mass of the object. This led us to the equivalence principle, which based on the observation that all bodies fall at the same rate, accelerate in the same manner from the same height above the Earth's surface, led us to propose that the gravitational inertial masses of all bodies must be the same ratio. And by absorbing that numerical value of that ratio into Newton's gravitational constant, we could take the gravitational inertial masses to be equal. So this is called the principle of equivalence of inertial and gravitational masses. Yeah. Then we also briefly spoke about the normal reaction and gave an example of a person in an elevator that is accelerating upwards, and discussed what a weighing scale would read. It would read a little bit more than the weight of the object, mg. We also spoke about a couple of other examples of forces. One was the electrostatic force given by Coulomb's law, which is very similar to Newton's law of gravity, except that can be both attractive and repulsive. And then, depending on the nature of the charges, we also talked about some macroscopic forces that are very familiar and important, such as friction, viscous force between layers in a fluid. Yeah. And we said that these are macroscopic manifestations of electric forces. For that matter, even the force in a stretched string, or the force in a pendulum rod, these are all obtained by many repeated uses of superposition principle of forces due to microscopic constituents, molecules, atoms, electrons. Now, for this reason, the electric force is called a fundamental force, while friction and viscosity are called emergent or phenomenological forces. As somebody pointed out, friction and viscosity are also examples of contact forces. They are present when bodies are in contact. And I emphasized that though these emergent forces arise from electrostatic interactions, it is often not practical to deduce their strength from microscopic considerations. It is hopeless. It's a very difficult task. One does it if you really need to, through large-scale computation and so on. They are usually described via effective macroscopic laws or formulae based on experimentation and experience, like Hooke's law for a spring. That to some approximation, the force that a spring exerts is proportional to its extension. Now, that is not exactly true. It's only true for small extensions, but it still is a useful rule of thumb. Not quite accurate within its domain of validity. Now, the drag force on a sphere moving slowly through a fluid is approximately proportional to the speed of that sphere. Okay, I say approximately because there are lots of other effects. It's not exactly linear in the velocity, but it points in the direction opposite to its velocity. So this is another example of a macroscopic emergent force. Again, very difficult to deduce based on interaction between water molecules and your sphere, or for that matter, neighboring segments of a stretched string are found to exert a tensional force on each other. So you may have a stretched string, here, a vena string, and you have, let's break it up into some segments. Now each segment, so let's look at the central segment. The central segment is tugged to the right by its neighbor and to its left by its other neighbor. So you have, these are called the tensional forces. So every bit of string pulls at its neighbors, tending to elongate the string. Such forces which tend to elongate go by the name of tensile. So it's called a tension. So tension it has units of a force. It's just a force. Yeah, but this is a tensile force. And in many cases, it can be approximated to be a constant. Yeah, of course, depending on the material of the string and so on, and how tightly it has been tied, and so on. Yeah, so that's an example of a tensile force. Can you give me the name for a force that is of opposite character? Tensile tends to elongate. What's the name given to one that does the opposite? Yes, so Kaustubh Manda as well as Aditi Mishra have given suggestions, perhaps even others. So yes, a compressional force. The compressional force is one that tends to do the opposite of elongate, tends to compress. Now, a spring, which is attached to a body and has been elongated, yeah, when it is let go, tends to compress. Yeah, so in that sense, a spring, a stretched spring tends to compress. So does a sponge, which has been stretched a bit, could also tend to compress. Yeah, that is true. So the general name for such forces are compressional. Yeah. The word stress is also used. Stress is another name for force. So we might call it a tensile stress or a compressional stress. So the word stress is synonymous with the force, and that is a good thing to know. Okay, any question? Okay, so there is some sort of tensile stress that we have also become aware of in recent times, the large scale of the galaxies and universe. Yeah, perhaps you have heard about it. So yeah, it goes by some fancy names. So it is believed that galaxies are flying apart from each other, and not just flying apart at increasingly rapid rates. So this is some kind of accelerated expansion. So perhaps that is ascribed to some kind of tensile force on a very large scale in the universe.
Or are you talking about dark energy?
Yeah, so that is another fancy name we give to it, indeed. So dark energy is the unknown thing that is postulated to be responsible for this tensile force on large scales in the universe. Indeed. Was that Krishan?
I couldn't understand this part.
Yes, sir. Yes.
Okay, good.
I could not understand this for this dark energy part.
No. The dark energy, I have not explained anything about dark energy. I am just saying that the observed behavior of the universe on large scales, I emphasize on very large scales, not on galactic scale, it's on much larger scales than our galaxy, is indicative of a behavior very much similar, somewhat similar to a stretched string. Yeah, in a stretched string, every part of the string is trying to get away from every other part of the string. Okay, so in my picture here, somebody is pulling at this string from this side and somebody is pulling from that side with some tensile force F on either side. Then every part of the string, no matter where you are, is moving away from every other part. And suppose the people who are pulling it apart don't just hold it fixed, they keep on pulling apart, stretching the string, then the resulting situation is somewhat similar to what seems to be happening with the universe as a whole. Now, we say that there is some energy associated with this tensile expansion, and that energy is called dark energy. So I don't claim to have explained it. I'm only making an analogy with something very concrete, so that it is clear to you that this is entirely possible. This is already a very graphically made explicit to you just on a string, which is being pulled on either side. Of course, here you have somebody to pull it. The universe, not clear anybody is standing on either side pulling it. So there is some kind of energy in the universe itself, which may be responsible for this tensile expansion. So that energy is called dark energy. Since we don't know much about it, we call it dark. Okay. Yeah. So I hope that is all right. Any further question? Yeah. So yeah, we'll say more about these things. There are other interesting aspects. Okay, so aside from gravity and the electromagnetic forces, which I have just briefly spoken about, there are two more fundamental forces. Yeah, I said gravity and electromagnetism are fundamental forces. The other things we have spoken about are sort of effective or emergent forces that are deduced from these. But it turns out there are two more fundamental forces, the so-called weak and strong nuclear forces. The latter, strong and weak nuclear forces, are very short range. They act typically over nuclear and subnuclear. Strong force acts over nuclear scales, and the weak force acts even over subnuclear scales. Yeah, I mean, this is just a rough description. And they are responsible for many interesting phenomena in atomic and nuclear physics, such as radioactive decay, and for the binding of neutrons and protons in nuclei. So the strong force is responsible for the binding of neutrons and protons in nuclei. Okay. So these are two more of the fundamental forces that we are aware of.
Sir, sir,
Yes.
sir, these are these forces non-conservative in nature?
No, to our knowledge, all these four forces are conservative forces. They are very, very, the non-conservative nature of forces arises because we, for our convenience or because of the nature of the system, we partition it into parts that we are interested in and parts that we are not paying attention to. And then some energy is lost to the part which we are not interested in. And then we model what is rest as a non-conservative force. So when you drag a object on a surface, I mean, overall energy is conserved, but some of it is converted into some heat and other, or into molecular motion, and we don't want to pay attention to that molecular motion. So then we model it by a force that is not conservative. But the electric force itself is conservative, so is the magnetic, and I mean, they are all conservative in the sense that they all come with some conserved energy overall. I'm not saying they necessarily come as the gradient of a potential. One needs to generalize that concept slightly, but in all ways you would like to believe they are conservative. So conservative systems and forces are extremely important from a fundamental physics point of view. However, when we deal with actual systems, especially macroscopic systems, we definitely need to understand frameworks where friction and viscosity and other dissipative mechanisms are important and dealt with. Okay, any other question? Okay, next, let us introduce some more concepts. I mean, I have been cavalierly using the word energy. What do we mean by it? At least in some simple context. So let us come towards such matters. So first of all, so this is our next topic. I'm going to talk a little bit about momentum, energy, work, angular momentum, and generally what we mean by dynamical variables. Okay, so now the linear momentum of a particle of mass m moving at velocity v is defined as p equal to mv. Okay, that's all. Now, of course, we are restricting attention to inertial frames. That is where we are talking. Our setup is now if there is no force, then each of the components of momentum, that is px, py, and pz, is conserved because the rate of change of momentum is equal to the force by Newton's first law. Sorry, I mean, that's Newton's second law, but according to Newton's first law, if there is no force, then the rate of change of momentum is 0. So the absence of a force, every component of momentum is independent of time, and we say that each component of momentum is conserved. Now, it may happen that the force only acts downwards. Yeah, so F has only some, let us say, Fz z hat component. Then it will still be the case that the horizontal components of momentum, Px and Py, would still be conserved because Fy and Fz, Fx would still be 0. So Px dot and Py dot will both vanish. Yeah, so all right, so that is as far as momentum is concerned. It's a familiar concept. I mean, there is more to momentum, but we are just introducing ideas right now. Okay. Let's now recall the work done by a force So this is something we are already familiar with somewhat. So let me quickly recall for you. That suppose a particle is moved from a position A to position B along a trajectory R of t. You can call that trajectory gamma if you like. The position vector of the particle along that trajectory is R of t over a time between T0 and T1. Then the work done by the force F of R, the force is a force field, of course, is defined as this line integral. We have met it before. W of gamma is equal to the integral F dot dr over the curve gamma. So you can write it as a one-dimensional integral dt over here, dr dt times dt. As already noted, this work depends on the trajectory and not just on the endpoints, namely A and B. Generally, for a general force, it depends on the entire trajectory. So this picture should help as well. Particle begins here, ends over there, traverses this path. At any point along the path, there is a force acting on it. Of course, the force need not point tangent to the curve. There is no such requirement. Of course, at any point along the curve, there is the infinitesimal displacement vector, which I call dr. And the dot product F dot dr is the infinitesimal work done. Integrating it to get the total work. Okay. However, there is a special situation, special class of forces where this work depends only on the endpoints. This is something we talked about. In fact, suppose the force field is given by the negative gradient of a potential function. Okay, so this is conventional, that F is equal to minus gradient of some V. So remember, minus gradient of V is a vector with components minus dV by dx x hat plus, so there's minus overall, dV by dy y hat and dV by dz z hat. So these are all partial derivatives to make the distinction with the ordinary derivative dV by dt, for instance, because V is a function of R, which is a function of t. So when I differentiate with respect to time, I will use the ordinary derivative d by dt. When I differentiate with respect to the three different arguments, I will use partial derivatives. Yeah, so I usually call them partial V partial x or dV dx. Some people say dou V dou x. Yeah. Different people have different names for it. Different states, sometimes people call it by different names. Anyway, but partial is the most commonly used.
So what have you written here? This, which is seen to be the drop in the potential.
Yeah, I have not yet come. So just a moment. Yes. So I just defined for us recall for us the potential. Sorry, the potential and the gradient of the potential. So suppose the force is given by the negative gradient of the potential. Okay, then the work done. The work done, let us compute W of gamma, is for the force I am going to substitute minus grad V and then dot dr dt. Yeah, but then you notice that this dot product is in fact equal to dV by dt. And how do you see that? If you take the dot product of grad V and R dot, I'm writing it out, the three components of partial derivatives of V and the three components of dr dt, take a dot product, you see it is partial V partial x dx dt plus partial V partial y dy dt plus partial V partial z dz dt. But that by the chain rule is simply the total derivative dv dt. Okay, so I am integrating with respect to time minus of dv dt. Now, this is just a very ordinary integral which you have seen before, integral of a derivative, one variable integral. So it is simply the function evaluated the endpoints, taking account of this minus sign. I will get v at the upper limit minus v at the lower limit, but of course I have to reverse the sign, so I'll get v of a minus v of b. Okay, so what is the summary? The work done by the force is the difference in potential energies at the two endpoints. More precisely, it is the potential energy at the initial point minus the potential energy at the final point. So in English, we would say that this is the drop in the potential energy. Whatever it was, what it became, the difference. So we see that the work done is the drop in the potential energy. Yeah. So that was what you were asking, I think. Yeah, Ankon.
Yeah, I was asking that.
Yeah, I hope it is clear. We're just interpreting the formula. That's all.
Okay. Okay.
Yeah. Anyway, it's a nice slogan to have in mind, that the work done by a force, conservative force, is simply the drop in the potential energy. V is called potential energy or potential. Different people use, I mean, different sentences I will use different names for the same thing. Okay, so that is the concept of the work done by a conservative force. From there, now we can move to the conserved energy for a conservative force. Okay, so let us see what that is. This is a nice concept. Now, many interesting forces, such as the gravitational force, the electrostatic force, as we said, and somebody also pointed out, maybe Krishna, I forget, as well as the simple harmonic restoring force in a spring, are all conservative forces. Okay, in all these cases, the force is the negative gradient of some potential. Of course, this is not true about friction. Yeah, so yeah, it's not applied to every force. For such conservative forces, Newton's second law can now be rewritten. mr double dot is equal to the force at location r, which is minus gradient of v of r.
Sir.
Yes.
I had a question that if you take f to be minus of gradient v, then you will see that the work done depends only on the endpoints. But is the converse true?
Depends what you mean by the converse.
I mean, if the work done depends only on the endpoints, then I don't think it will. F will always be of the form minus gradient of v.
No, there is such a result you can show. Yes, if the work done, I mean, not just for one path, but for every path. Yeah, you need a rather strong assumption. If the work done by the force along every path, joining any pair of points in your space, depends only on the difference between these. Yeah, I mean, it depends only on the endpoints. Then one can establish that the force, there must be some function of which the force field is a gradient.
So how will you prove it?
Yeah, okay. Maybe I will develop that as a problem or something. I'll try to indicate that for you. Yeah, I don't want to try to do it here now, but it is something one can establish.
Okay.
Sure.
Okay.
Yeah, it's a nice result about vector fields. Yeah. Yeah, and it has nice applications in thermodynamics also, and yeah, so it's a nice thing. We will talk about it when possible.
Can you move up a little bit?
Yes. Is this what you were looking for?
That's okay.
Yeah. So, by the way, I wanted to mention, I'm not sure all of you are aware, but the notes from lectures are available on the website of the course, and you are expected to keep up to date with whatever we have discussed in the classes. Okay. Yeah. Now we were going to talk about this energy. So here we are. So we've rewritten Newton's second law in this manner. Now we will see that this form implies that a sum of a certain kinetic and potential energy is conserved along trajectories. So let me explain. So first of all, I am going to introduce a concept, energy E equal to half m r dot squared plus v of r. Yeah. R dot is simply the velocity. So this is half m v squared if you like. But there are too many v's here, v for velocity, v for potential. Yeah. So let us see why. So we'll do this in several ways. One way is to simply differentiate and show it is independent of time. So let us take this formula for energy, proposed energy, half m r dot squared plus v of r, and differentiate it in time. Yeah, this gives us a nice chance to learn how to differentiate vectorial quantities. So what is it? E is, there are two terms. Let's deal with each one. Half m r dot dot r dot, right? That is what r dot squared means, plus this v, of course. So I'll call this T plus V. T is the name given for kinetic energy often. That's the first term. Sometimes we call it K also, T or K. K for kinetic energy. Now, if I differentiate the kinetic energy, I'm going to get two terms. One when I differentiate the first r dot, and second when I differentiate the second r dot. So I'm going to get half m r double dot dot r dot plus half m r dot dot r double dot. Okay, I'm avoiding the vector symbols, but they are understood here. Let me reinstate them. Okay, so this is how you differentiate a product, dot product of two vectors, because after all, a dot product is a sum of products. So we have to use the product rule of differentiation. Yeah. And that's going to give you two terms, differentiate first times second plus the other way around. Combining all the terms, the result is again a dot product. Now, these two terms can be combined because the dot product has an important algebraic property of being what? What property of the dot product?
Commutative.
Indeed, it is commutative, and therefore I can write this as m r dot dot r double dot. Okay, the two terms are combined in this manner. Yeah, and that's what's been written here, m r dot dot r double dot. Okay, so much for the derivative of the kinetic energy. As for the potential energy, let us do the same thing. The potential energy is V. I just need to compute each time derivative. Well, you have to use the chain rule. Remember that V is a function of R, which is a function of time. So if I want to find V dot, I will have to first compute dV dx, x dot, plus dV dy, y dot, plus dV dz, z dot, and observe that this sum of these three terms is actually the dot product of the gradient with the velocity vector. I hope you are able to see this. Any question? Please do check and tell me. Okay, so there we are. We have computed the derivatives of kinetic and potential energies, we notice that in both the terms, there is this common factor of r dot, namely the velocity. So let us take that out. So there's a velocity taken out, dotted with the remaining stuff, which in the first case is mr double dot, and for the potential is simply the gradient of v. So there we are. This is dE dt. So we are almost there. So we have shown that the rate of change of this so-called energy is the velocity dotted with a certain vector. Now, do you recognize the quantity in parentheses? What is that?
0.
Yeah, it's simply 0 because that is simply the Newton's second law, which is saying mass times acceleration minus the force, but that quantity is 0 by Newton's second law. Okay, so using Newton's second law or the equation of motion, we have shown that E is conserved. We have shown that E is constant along a trajectory. Right? We have made use of the equation of motion. So this is valid only along a trajectory, not around any path. Cannot assert this about arbitrary paths. Assuming, of course, that the force is conservative. That again we have used here in recognizing this as Newton's second law. Otherwise, this grad V formulation would not work. Now, so a curve qualifies as a trajectory provided it satisfies the equation of motion, mr double dot equal to f. Okay, so only such curves are called trajectories. Okay, very good. So now we say that the energy is a conserved quantity. So finally, what is the formula for energy? It is basically half m r dot squared plus v of r. Okay, so this is a very simple and nice formula worth bearing in mind. We say that the energy is a conserved quantity or a constant of motion. Constant of motion in the sense that it doesn't change as the system undergoes its dynamics. If the forces are conservative, that is expressible as a gradient of a potential. So under those circumstances, the energy is conserved. Yeah. So the point is that those forces I spoke about, electric and gravitational, they have some associated energy. That energy formula is more complicated than this. Yeah, but nevertheless, I mean, there may be more than one particle or several charges present. You may have to include the energy in the electric field, yeah, so on. But anyway, when you do all those things, turns out there is a conserved energy. Okay, this total energy is sometimes also expressed in terms of momentum. P equal to mr dot rather than velocity. So if we do that, we will replace by P upon m. And when we do that, the energy becomes P squared upon 2m plus V of r. Okay, so this is just another way of writing the energy now as a function of the position and momentum. Previously, we wrote it as a function of position and velocity. Okay, they're just basically the same thing, different variables being used. There is a significance to this, which we will talk about later if possible. But in this latter form, where momentum is used in place of velocity, the energy is sometimes called the Hamiltonian function. So this is just some name that I'm introducing now, but you might as well hear it. The energy, when expressed in terms of momentum rather than velocity, usually is called the Hamiltonian. It has a deeper significance, which we will come to later on. All right. Now, one can obtain this conserved energy by other means as well. What did we do here? Somebody gave a proposed formula. We differentiated, checked it is 0. So we concluded that E is constant. Constant along trajectories. But you may ask, how did we come up with this formula in the first place? Yeah, so I'll give you an indication of how it can be done. Can be done essentially by integrating Newton's equation of motion once using a so-called integrating factor. Okay, so has anybody heard of an integrating factor? Come across such a concept?
Yes, sir. Differential equations.
Yeah, in differential equations, you may have heard of an integrating factor. Well, if you have not heard, no problem, because you're going to hear about it in the next 1 minute.
Let me explain this point again. What do you mean by one can obtain this conserved energy by integrating? What are you trying to say actually?
Yeah, what I am trying to say is that I gave a proposed expression for energy. This expression, half m r dot square plus v of r. Okay. Now you may ask me, where did I come up with this expression? Yeah, is it some inspiration? Is it some guess, or somebody told me? Yeah, or all of the above? Yeah. So I'm giving some inspiration now as to where this formula came from. And in some sense, all formulae have to come from the basic laws. So in this case, the relevant. So let us see how, starting from mathematical methods, namely that of integrating factors, we can arrive at this energy. Okay, so that's all I mean. I'm going to do it in a moment. Now, the name integrating factor is given to a quantity that somehow helps you to integrate an equation, a differential equation. Okay. So, fine. Let us see this idea in action. So, for simplicity, consider motion on a line that is 1 degree of freedom, particle moving along a line. Yeah. For a conservative force field, the force is written as minus v prime of x. Okay, so I don't need all gradient and all, just the ordinary derivative with respect to x. It's only one spatial coordinate. And Newton's equation of motion, which is mx double dot equal to force, becomes mx double dot plus v prime of x equal to 0. Remember, the force is minus v prime of x, and I brought it to the left hand side. So this is our equation of motion. You will notice that our proposed energy expression involves only first order derivatives. Yeah, only r dot, no r double dot. So that suggests that we have to somehow integrate Newton's equation once, because Newton's equation is second order derivatives. But we want only first order derivatives, so we need to integrate it once. Moreover, this energy involves the velocity in quadratic order. That is the square of velocity. So these are some observations which will help us. So the idea is that we start with our Newton equation, mx double dot plus v prime equal to 0, multiply it by the velocity, x dot. So let's write down what we get. Mx double dot times x dot plus v prime of x times x dot equal to 0. Just multiplied by x dot. So, but now something nice happens. We recognize that this expression is actually what is called a total time derivative. This mx double dot x dot is actually the derivative of half m x dot squared, right? Using the product rule of differentiation, the two cancels out, get x dot times x double dot. Hope you're able to see that. And similarly, this v prime of x times dx dt t is simply dv dt. Okay, that is again by the chain rule. So combining these two, we recognize Newton's equation upon multiplication by the integrating factor as the time derivative of some quantity being 0. That quantity, lo and behold, is the energy, half mx dot squared plus v of x of t. Thus, the total energy E, namely half mx dot squared plus v of x, is conserved. So this is a way to discover the energy from the equation of motion. You need a little bit of inspiration. You need the right integrating factor. But you will see this in other examples also, and you will become good at it. This idea is very general, works for many types of differential equations. Okay, any question about how we went about this? Okay, if not, let us just summarize what you have got. So the total energy is energy, or total energy is the sum of a kinetic energy half m x dot squared, which accrues, which comes from the particle's motion. Okay, so kinetic energy is the part that depends on the velocity, very roughly speaking. Okay, comes from the particle's motion, and another part goes from the conservative force, so that was its origin. All right, so that's the energy. All right. Now, I hope you have digested this summary so far. If you have a conservative force, namely F is gradient of some potential or negative gradient of some potential, then there is a conserved energy, which is the sum of kinetic and potential contributions. Right? Okay. Now, let's look at a nice related result, which is called the work-kinetic energy relation, or work energy theorem, various names. Now, so for some very different character in conservative. Okay, so I'm not making any assumption about the force being conservative. No potential function may be available. Yeah, but we are going to make use of this concept of kinetic energy that I have introduced just now. Yeah, introduced a concept of kinetic energy. That concept makes sense whether or not there is a potential energy. I'm not saying it's conserved and so on. It is simply a formula. And consider it. See how we can interpret it. Okay. So what we're going to show is that the work done by a force while moving a particle along a trajectory can be expressed as the increase in kinetic energy. Okay, so this is the result we are going to establish in a moment. Previously, what we established is that the work done by a conservative force is equal to the drop in the potential energy between the endpoints. Now we are going to show that it is equal to the increase in kinetic energy between the endpoints. Okay, so somewhat different roles are played by kinetic and potential energy. And in this new result, Potential is not mentioned at all. There is no assumption of a conservative system. Yeah. Okay, so I hope you're clear about the setup. So now, suppose, and we will do a little bit of gymnastics and show how this can be done. Suppose R of t is the trajectory for some times between TA and TB, where the particle is moved from A to B, configuration or position B. Okay, then using Newton's second law, we can compute the work done along this curve, along this trajectory. Well, what is it? It is integral TA to TB f dot dr dt times dt. Okay, so this was our formula for work. Now we're going to use Newton's second law. According to Newton's second law, of course, all inertial frame, force is equal to rate of change of momentum, dp dt. Now dr dt is the velocity, so I write it there as velocity. So it's a dot product integrated in time. I'm omitting the limits of integration because the same thing. Okay, so now we can cleverly combine these terms. Recall that P itself is mv. Yeah. Please do ask if you have any question. P itself is mv, so I put that in here. D by dt of mv dot v dt. Okay, so can take the m out. It's a constant. Remember, masses of particles are postulated to be independent of time. So we'll get m times. See this dt I'm going to cancel and think of it as a dv differential. So we have m dv dot v. That's what's left over. M v dot dv. Okay, so so now what is this? This is integral m vx dvx plus m vy dvy plus m vz dvz. Okay, this is the sort of integral we have. You will notice that each of the terms is very simple. This is m d of 1/2 vx squared, yeah, plus m d of 1/2 vy squared plus m d of 1/2 vz squared. Yeah, hope you can follow. And now I can combine all three and write it as integral of 1/2 m d of vector v squared. Yeah, vector v squared will be vx squared plus vy squared plus vz squared. When I say vector v squared, I simply mean v dot v dot product. Okay, any question? My computer is asking a question. So if you don't ask, computer will ask. Okay, fine. So here we are, and now we are ready to do this integral. I mean, it's again an integral of a derivative, so it's just the value of this quantity evaluated at the endpoints. So we would get 1/2 m vb squared minus 1/2 m va squared. Okay, so that's what I have given over here as the final answer. We have this remarkably simple and elegant result. The work done by a force, no assumption about being conservative has been made. Of course, we have assumed that it is a trajectory, so Newton's second law has been used. And we have been able to express it as a difference between kinetic energies at the two endpoints. Okay. So this is this work energy theorem. I would like to make a couple of comments about this, slightly subtle comments. So please try to follow. Don't worry if some things are lost on you. Let us contrast this formula. By this formula, I mean this formula for the work which you have just now derived. We have now two formulae for the work. One done by a conservative force, which depends only on the difference in potential energies at the end points. Yeah, that let me recall that formula for you. Here it's W of gamma is equal to VA minus VB. That is one formula. And now we have a second one where W of gamma is kinetic energy at B minus kinetic energy at A. Okay, so all right, so this is the work done. So I claim that despite appearances, the right hand side of the new formula that we have derived, where we made no assumption about the force being conservative, generally depends on the whole trajectory and not just on the endpoints A and B. Okay, there is a sense in which even though W has been written as a difference of kinetic energies at the endpoints, in effect, one needs to know the entire, I mean, it depends on the whole trajectory. Yeah.
So why contrast? I mean, if the force is conservative, then this difference of kinetic energies will be equal to the difference of the potential energies. So that would be another way to show that for conservative force, the total energy is conserved.
Yeah, you're right. Absolutely. So you could equate these two
So I was
formulas.
saying that contrast. I mean,
Yeah. So look, Ankon, you are asking a very relevant question. There are many issues we can discuss over here. So let us do them one by one. Okay, let us start with simple things. Maybe I'll do it on a separate page. Get rid of this. Yeah. See, we have shown that conservative we have a conservative force F is equal to mod V, then the work done along trajectory is equal to VA final points. Then we have shown that generally, independent of whether it's conservative or not, W of gamma is given by half M VA, sorry, VB squared minus half M VA squared. Okay, so true in general trajectory. Okay, so now propose working with a concept. So if force, then both these formulae must hold. Yeah, both formulae must hold. So equating them, equating W of gamma in the two approaches, yeah, W equal to W will imply that, let me take the first step of moving of MVB squared minus half m VA squared. Okay, so taking it to the other side, we will get that half m potential at A is equal to half m VB squared plus potential at B. Okay. And now we would say that this is true for any trajectory between any pair of points. Yeah, I mean, you have some trajectory, you're not obliged to start and end there, you're not in the middle and end somewhere else, etc. Yeah. This is equal to that is valid for all points along the trajectory, and therefore this itself, therefore the quantity half m r dot squared plus v must be constant trajectory. Yeah, and therefore we have now discovered that there is a conserved quantity along the trajectory. This constant of motion is called energy. So, in other words, we have derived energy using this work energy principle. Okay, so okay, so but there is more to the story. What if the force is not conservative? Then we cannot. I mean, there are two expressions. The space holds, but the first expression, the comment I was making concerns the second circumstance where the force may not be conservative. Yeah, it's a somewhat subtle point, and I'm afraid I may not be able to convey it without a little bit of effort. I claim that this velocity squared minus velocity squared in effect determines the, but for a non-conservative force, we already said that generally the work would depend on the whole trajectory, not just the endpoints. So you may wonder how, for a general force, I'm able to get such a formula. How can I get such a formula that seems to depend only on the endpoints? Okay, that's the question I'm asking. Is my question clear? Is the puzzle clear?
Your words are getting very internet. I think
How for
I don't know if
agents?
it's happening with others, but I mean, your words are coming very discreetly. Can you repeat your question?
Okay, I'm sorry. Let me repeat myself. We asked the question. See, here we have derived a formula for the work done by the force, W of gamma. We have not assumed the force to be conservative. It considered a general force. We already observed that for a general force field, there is no reason that the work done should depend only on the endpoints. It will generally depend on the entire curve traversed, the entire trajectory. Yeah, that was on general grounds. We came to that conclusion. Having come to that conclusion, now we have got a formula that seems to violate that conclusion. This formula seems to depend only on the endpoints. Yeah, seems to depend on the velocities only at the endpoints. The endpoints and the velocities at the endpoints. How could this happen? Okay, so this is the puzzle. Yeah.
But the integral that have you kept the integral to this formula? Sir?
Wait, I didn't catch what was said about. Yeah. Yes, please repeat.
Get from the integral to this formula.
See, wrong with the derivative. No, okay, you're asking how did we take step? I mean, the way we have taken this step is simple, just integration. I mean, the rules of integration. I hope that is not under question.
Assuming the fact that integral exists, isn't it the same as assuming that the force field is conservative?
I mean, yeah, that okay. I mean, we are just discussing freely here. Yeah, I mean, on the face of it, we have got an expression for the work done for the force that's depend only on the endpoints. Work cannot be dependent only on the endpoints. It has to depend on the details of the curve. There is a resolution to this puzzle, and that is what I'm trying to discuss here. It is a subtle matter, not very complicated. Yeah, but I hope the puzzle at least is clear. Leave alone the resolution of the puzzle. This was not supposed to happen. Yeah. Okay, let me clarify why it is okay. See, the point is that Newton's second law is second order equation of motion. Is a second order equation of motion. Okay, so it requires two initial conditions, namely the initial position and the initial velocity. If you give the initial position and velocity, then the entire trajectory is known. Yeah. So in this case, if we know the position as well as the velocity, then you know the whole trajectory. So in this formulation, even though it looks as though it depends only on the initial and final locations, that is not true. It depends on the initial and final locations as well as the velocities at those points. For that reason, this formula for the work done has in fact enough information to determine the entire trajectory. Because if you know the potential, sorry, if you know the velocities at the end point as well as the initial location, you can find the whole trajectory simply by integrating the equation of motion with those initial conditions. Okay, so we have to contrast this formula. This formula depends on velocities. While the earlier formula, namely W of gamma is equal to VA minus VB, does not depend on velocities. And that's what we said. For a conservative force, can depend only on the endpoints. Here, for a non-conservative force, it has to depend on things more than the endpoints. And that is indeed the case. It depends on the endpoints as well as the velocities at the endpoints. Okay, so that is the resolution of this little puzzle. I will let you think about it a little bit. It's nothing very complicated. I invite you to think about it. But please let me know if you have any immediate questions now. Okay. If not, yeah, I was going to discuss the angular momentum, but that will come next time. Okay. If not, we will stop here and meet again on Thursday. Any other urgent matters?
Can you say anything about the exam?
So according to the schedule, it is on Thursday, 29th September. That is next Thursday in the afternoon. So further details, I will communicate them with you. Yeah. So don't worry. I will communicate any further details to you. Yeah. Anything else? Okay. So have a good afternoon then, and we will meet on Thursday. Thank you.
Sir,
Yeah. Yes.
Physics.
Please repeat yourself, Anhan.
Could you please, are we going to have a mid-semester exam for physics?
So that the timing has already been announced in the by the registrar. So we will respect that timing. I will give details about the format and so on. I will communicate that to you as soon as possible. Yeah. Any other doubts about this? Okay. By the way, there was some suggestion about Bernoulli's equation. I don't recall what context Chandralekha has suggested this. So please clarify this for me. I did not notice this comment. For the integrating factor. Okay. All right. Yeah. So there are other differential equations where you can use similar ideas. Okay. That's a nice point. Okay. Thank you. Any other comments? Okay. If not, we will stop here. Thank you for your attention.